everybody, and welcome back for Unit 5, Lesson 4, which is about points of inflection and concavity. We have one learning target for today, and today's learning target is I can use the second derivative of a function. So this is going to be a little bit different. Up until now, we've been focused on the first derivative. So now we're going to change gears and look at the second derivative to find information about a function, including the location of the points of inflection. So we're going to have a new vocabulary term here, points of inflection, and the concavity of the function, which we've actually talked about before, and we're going to review today. So we're going to be looking for concave up versus concave down. Okay, let's start by looking at concavity. So we've talked about concavity before as the curvature of a graph. In this lesson, we're going to be talking about finding intervals where the function is concave up and intervals where the function is concave down. When we describe intervals of concavity, we always use open intervals. This means that no matter what, all the time, you're going to be using open intervals. So, open intervals means you're going to be using parentheses all the time when we're describing concavity. So let's start with concave up. A function is concave up on an interval when we look at the graph and it's shaped like a cup. So concave up, we usually visualize looks like this. Now, it doesn't need to be a full cup. So it could be a part of a graph that looks like this, which would be like just the left side of the cup would still be considered concave up. Or it could be a part of the graph that looks like this, which would be just the right side of the cup, would still be considered concave up. So if I was to highlight the parts of this graph that are considered concave up, it would be this part right here, because that part is shaped like a cup. And then the concave up part would kind of stop right here because it kind of switches to being shaped like a frown, which we're going to call concave down. And then also this part of the graph over here is concave up because it's shaped like a cup. If I were to list those intervals, I would say that the intervals are -3, 0 for the first one and 3, 6 for the second one. So the next thing we're going to look for is where the graph is concave down. Now, a graph is going to be concave down when it is shaped like a frown. And I know that this sounds kind of cheesy, but it really does help you remember. Concave down is when it's shaped like a frown. So that's going to be when the graph looks like this, like a frowny face. Or it could just be one piece of that type of curve. So it could be the left side of the curve where it's concave down, or the right side of the curve where it's concave down. In this case, it would be this middle section of the graph right here, which is shaped like a frown. We would say that that is concave down, and the interval would be from 0 to 3. And you'll notice that for all of these intervals for concavity, I'm using open brackets. Open intervals, which are parentheses. So we're not including the endpoints here. Now we're going to add in a new vocabulary term because we have talked about concavity before, a new vocabulary term which is called points of inflection. A point of inflection is going to be a place on a graph where the graph changes from concave up to concave down or vice versa. So the graph of the function has to actually change concavity in order for us to have a point of inflection. On this picture, the points of inflection would occur at 0 and at 3. So in this example, it would be at x equals 0 and x equals 3 because the concavity of the graph changes at those x values. We switch from concave up to concave down or concave down to concave up. Each of those points is called a point of inflection, and this is the really important part. In order to be considered a point of inflection, it must be a place where the concavity actually changes. Now, what I want to point out is that this is different from how we define a critical point. A critical point was when we looked at the first derivative and we looked for a place where the derivative was equal to 0 or does not exist. In this case, for a critical point, it did not necessarily have to be a place where the function actually changed from increasing to decreasing or vice versa. We never said that. It was just a place where the derivative was equal to 0 or does not exist. Points of inflection are different. Points of inflection, it has to be a place where the concavity changes. If the concavity doesn't change, then it doesn't count as a point of inflection. So let's see if we can define this in terms of the derivative. So what is the relationship between derivatives and concavity? A function is going to be concave up when the second derivative is greater than 0, so is positive. So we can tell that a function is concave up when the second derivative is positive. A function is going to be concave down when the second derivative is less than 0, which means, in other words, it's negative. And a point of inflection is going to occur when the second derivative changes signs. Now you'll notice that unlike critical points, we did not say that a point of inflection happens when the second derivative is equal to 0 or undefined. It has to be a place where the second derivative changes signs in order to be a point of inflection. So how can we analyze a function using derivatives to determine concavity? First, you're going to find the second derivative. Now, this is really important. We need to use the second derivative, so we need to start by finding the second derivative. Then we're going to set the second derivative equal to 0 and solve. And we could also look for places where the second derivative does not exist. So if there is a place where the second derivative, there's a certain x value that you can't use for that derivative, you could also include that in your list. Then, just like we did for the first derivative, we're going to make a sign chart. So we're going to use our values from step 1 to divide the table that we make into sections. And we're going to test a value from each section by substituting that value into the second derivative. So this time, instead of plugging our numbers into the first derivative and looking at the signs, we're going to be plugging our numbers into the second derivative. Now, just like with first derivative stuff where we're looking at increasing, decreasing, and critical points, with second derivative stuff, how we justify our answer is really important. So the same rules apply. Do not use pronouns. Your sign chart is not enough. You have to actually refer back to what's happening with the second derivative in order to justify your answer. An example might be f of x, the original function, is concave up on an interval because the second derivative is greater than 0. Now, I do want to point out there is a typo here. This would be an open interval if you were really doing this problem, because for concavity, we're using open intervals all the time. Okay. Let's take a look at an example. So we're going to find the x-coordinates of the points of inflection and determine intervals where the function is concave up and concave down by using the second derivative. Step number 1 is to actually find the second derivative. So I'm going to start by finding the first derivative, which in this case would be 6x squared plus 6x. And then I'm going to take the derivative again to get the second derivative, which in this case would be 12x plus 6. Now I'm going to set that equal to 0. So if I factor out a 6, I get 2x plus 1 equals 0, which means x would equal negative 1/2. Now I'm going to make a sign chart. So the beginning of my sign chart would be negative infinity, and then I'm going to put the number negative 1/2, and then I'm going to put positive infinity for the end. And just like I did with my first derivative stuff, those numbers become the dividing lines of the sign chart. Now this time, however, we're going to be plugging those values in to the second derivative, not the first derivative. So we're going to be plugging these numbers into the second derivative, which means Instead of putting f prime here, I'm going to put f double prime, and I'm going to plug my values into the second derivative, which was already factored. Just like I would usually use the factored version of the first derivative, it's a little bit easier. If I pick a number to the left of negative 1/2, like negative 10 perhaps, and I plug that in, I have 6 times a negative number because negative 20 plus 1 is definitely negative. So that means that the original function was concave down like a frown in that section. Now, if I pick a number bigger than negative 1/2, like maybe positive 10, and I plug that in, I get a positive number, which means the original function was concave up like a cup in that section. You'll notice instead of drawing an arrow pointing down or an arrow pointing up, since this time the sign is telling me about the concavity, I'm drawing either a frown or a cup because it's not telling me about the slope. It's not telling me uphill or downhill. It's telling me the curvature, the concavity. Now let's figure out how to answer these questions, the points of inflection, concave up and concave down. So again, points of inflection are going to be places where the second derivative actually changes signs. Since I checked and the second derivative actually changes signs from negative to positive at the negative 1/2, I'm going to say x equals negative 1/2 is my point of inflection. And my reason would be because the second derivative changes signs. If I want to figure out where my function is concave up, I'm going to look back at my sign chart and I notice it's concave up on this interval right here. So my function is going to be concave up on the interval from negative 1/2 to infinity. And I would say because the second derivative is greater than 0. Now, I do want to point out we're not saying greater than or equal to 0, and that is actually the reason we don't include the endpoints here, is that we can't be equal to 0 for concavity. Whereas for increasing and decreasing, we could have a derivative that was equal to 0. That's why we include the endpoints. For concave down, I would look for where the second derivative was negative. So if I go back to my sign chart, it's going to be right here, which is going to be negative infinity, comma, negative 1/2. And I would say because the second derivative is less than 0. Now, just like we did with our first derivative stuff, where we looked at increasing, decreasing, and critical points, we need to be able to find this information when we're given the graph of the derivative instead of the graph of the original. So I think it'd be really helpful to compare the intervals on the graph of the original, where we are concave up, to the corresponding intervals on the graph of the derivative, and the same thing with concave down and points of inflection. So let's start with concave up. If we look at the original graph here, this graph is concave up between pi and 2 pi. Now, if we look at that same interval from pi to 2 pi on the graph of the derivative, you'll notice that that is where this derivative graph is going uphill. So what we usually say is that a function f of x is concave up when the slope of the derivative is positive. So the slope of the derivative is positive. This means we need to look for where the derivative is uphill or increasing. And that is how we would justify our answer. If you were ever asked to determine where a function was concave up given the graph of the derivative, you would say it's on this specific interval because the slope of f prime is positive. And this should make sense because the slope of the first derivative would be the second derivative. So in other words, concave up, which is the second derivative, would be positive when the slope of the first derivative is positive. Now let's talk about concave down. This function is concave down on this first interval right here between 0 and pi. And if you map that to the corresponding interval on the graph of the derivative, it would be where that graph is going downhill, or in other words, it has a negative slope. So we usually say that a function is going to be concave down when the slope of the derivative is negative. And again, that makes sense because the second derivative would be the slope of the first derivative. This means we need to look for where f prime is downhill or in other words, is decreasing. So this time, instead of looking for where the original is decreasing, we're looking for where the graph of the derivative is decreasing. Last but not least, points of inflection. Point of inflection, this should say point of inflection. The function f of x has a point of inflection. I am so sorry about the typos in this one. Inflection. When the slope of f prime of x changes directions. Now, if we look for where the slope changes directions, we can see that the concavity changes right here in the middle on this graph. And that would be the place on this graph where the slope changes from being a downhill slope to an uphill, or in other words, a negative to a positive. This means we need to look for maximums and minimums on the graph of the derivative. So we're looking for like a high point or a low point, because that's going to be the place where the slope changes directions. Let's practice identifying these places given the graph of f prime and then justifying our answers. Once again, it's important to realize that in this problem, we are given the graph of f prime. So this is not the original function. We're going to use the graph of f prime to answer questions about the original function, but we don't have that graph of the original to look at. The point of inflection is going to be the place where the slope of this graph changes signs. Now that's going to happen here, here, and here. We can see that the slope of this graph is positive and changes to negative, negative and changes to positive, positive and changes to negative. So we would say x equals -1, 1, and 4. And we would say because the slope of f prime of x changes signs. Now you're going to notice that in all of these justifications, we're always going to refer to the slope of f prime of x, because the second derivative is the slope of the first derivative. So if we've got the first derivative to look at, then in order to kind of analyze the second derivative, we need to look at the slope of what we've got. Concave up is going to be the portions of this graph that have a positive slope. So that would be this portion of the graph, as well as this portion of the graph right here. So we would say that this graph is concave up from -infinity to -1, and also from 1 to 4. And we would say because, you'll notice again I used open intervals for everything here, the slope of f prime of x is positive. So you'll notice again we referred to the slope of f prime of x, because if we're talking about the second derivative, it would be the slope of the first derivative. Last but not least, the original function would be concave down from wherever this slope is negative. So from here to here and here to here. So I would say that we are concave down from -1 to 1, and also from 4 to infinity. And I would say because the slope of f prime of x is negative. And again, you'll notice we're talking about the slope of the derivative, because the slope of the derivative would be the second derivative. All right, thank you guys so much for watching. That's all for today, and I will see you soon for some practice.